We saw during the last lecture that if we make a loop of wire, something like this, and run, we cause current to flow in this loop, and it is placed in a uniform magnetic field, then the net force exerted on the net magnetic force exerted on this loop would be 0. It doesn't mean that the object is not going to interact with the magnetic, this object with the magnetic field. It will actually interact. We will see today that there will be a magnetic torque exerted on that loop, and that this torque will depend on a quantity which we refer to as magnetic moment of this object. So I'll start actually the lecture with a more general definition of magnetic moment, not for any object, not just for a loop. If a magnetic moment is defined in such a way that if we place an object with magnetic moment mu into a magnetic field described by magnetic field vector B, then the magnetic torque exerted on this object would be equal to magnetic moment multiplied by magnetic field vector. Now, well, let's start it this way: that magnetic field here in this room, or actually on the northern hemisphere, magnetic field of the Earth is directed kind of well, it's northward and slightly down. So actually, in Kansas City, magnetic field has a vertical component and horizontal component. Horizontal component is directed toward the pole, a magnetic pole at the well, it doesn't coincide with the geographical pole. It is in Hudson Bay, and this is direction toward Hudson Bay. It is still pretty much northward from Kansas City. Now, let me give you a puzzle. We know that magnetic needle, where is the cursor? Okay. This is how magnetic needle is, will align itself in magnetic field. And we recognize, like I just said, let's say that this magnetic field vector is directed toward the north here in Kansas City. Well, this is how the needle would align. It will indicate with the north pole, it will align itself also in the same direction. So figure out what is magnetic moment of a magnetic needle. So for example, when it is aligned, it means that the magnetic moment exerted on that needle is, and when it is aligned, it doesn't tend to spin, right? Which means that what is the value of the torque? 0. Now, if we deflect, so let's say now that I'm the needle. Yeah. So let's say here my south pole, and this is my north pole. Yeah, so if I'm aligned with magnetic field, torque is 0. All right. Now, if I turn that way, or if somebody turns me that way, what will be the direction of magnetic torque? Well, I would tend to turn this way, right? So what is the direction of magnetic torque then? Well, must be down. Following the right-hand rule, it is down. Yes, so magnetic torque now is down. Down magnetic torque will turn me this way. Now let's say that I will turn myself this way. Well, the magnetic field will try to turn me that way, which means that torque is which way? Up, correct. Now we can even think different ways. Yeah, if I'm turned that way, what will be the direction of magnetic torque? Well, it will be away from you. And if I turn this way, it will be towards you. All right, so from those 5 situations, let's try to figure out what is the direction of magnetic moment. Yeah, right now, we will have to get a 0 torque. Now, magnetic moment is of an object is something. It's like an attribute of an object. It is a certain constant vector assigned to that object. Now, for an object, we can actually even change it. But for example, for electron, we cannot change magnetic moment of an electron. So changing moment of an object would require that we alter the object. We have to make some changes to change the orientations of particles constituting the object. All right, but if magnetic moment, and actually every magnet will have also magnetic moment. So let's say that magnetic needle has a certain magnetic moment. So in this configuration, magnetic torque is supposed to be 0. So what can you say about magnetic moment? What should be the orientation of magnetic moment? Madhumira, do you have an idea? Well, let's try different way. So let's say, just give me an arbitrary direction, and we will see if it works. Andrew, why don't you give me just anything?
Into the board.
Into the board, so perpendicular to the needle, right? So what? Okay, so my North Pole was that way, right? So if the North Pole is this way and South Pole is this way, let's say that my magnetic moment is into the whiteboard. Well, if it is into the whiteboard, magnetic moment is into the whiteboard, magnetic field is to the right. So if I use the right-hand rule, I would conclude from this formula here that magnetic moment should be down, which means that the needle would tend to turn this way. Is it the case? No, which means that magnetic moment is not perpendicular. It's not perpendicular to the needle. Let's try something else. Oscar, why don't you try another direction? Which way? Which way? Same direction as the needle? Always, or just in this configuration? In this configuration. Okay, let's see what will happen if the magnetic moment is in the same direction as the magnetic field in this configuration. Well, if the two vectors are parallel, their vector product is going to be 0. Oscar says that it's 0. And indeed, it is 0. Yeah, because just think in terms of magnitude. What is the magnitude of the torque? Magnitude of the torque would be magnitude of the magnetic moment times magnetic field strength times sine of the angle between the two vectors. And if they are parallel, angle is 0, sine of 0, angle is 0, so we can recognize that if magnetic moment is parallel to magnetic field vector, magnetic torque is a 0 vector. Well, but Oscar left us with ambiguities, yeah, because now, so at least this situation agrees, right? However, can we find any other, well, so right now actually we have two options. It is that magnetic moment is in the direction of magnetic field because this makes it parallel, or opposite. Actually, if it is opposite, then we will formally we will have sine of 180 degrees when we calculate the magnitude, which also happens to be 0. But no matter what, we see that in this configuration, magnetic moment has to be either in the same direction or in the opposite direction as the magnetic field vector. All right, can we find any other That's good. We can't. We can't. However, we have ambiguity. Now we have to determine, is it in the direction of magnetic field or is it opposite to the magnetic field? Is there somebody who believes that it should be in the direction of magnetic field and can give an argument? Would you like to try? No? Oscar, how about you? Can you try? Well, I will give you a hint then. Think what would happen if the needle slightly deviates. In this configuration, slightly deviates from the orientation of the magnetic field. So if the needle slightly deviates, it means that magnetic moment will also make a tiny angle with the magnetic field, and see what will happen in both situations. Well, let me do that. So if let's say that the needle turns slightly up. Yeah, this way. I mean, with the angle up. Yeah, so now, if magnetic moment were aligned with the field, well, so vector product of magnetic moment, which is in this direction, and magnetic field, which is in this direction, results in a downward product. So torque is downward. What the needle will do then? Turn this way, right? The magnetic torque is trying to push it this way. Let's now see what will happen if if the needle deviates slightly this way. So magnetic moment is in this direction. Now magnetic field is this direction, so torque is up. What the needle will do? Turn this way. Try to come back. All right. Now let's see then what will happen if magnetic moment is in this direction. So now you have to think that this is North Pole and this is South Pole. However, we assign magnetic moment in the opposite direction. And let's say that I deviate slightly to the right, which means that now magnetic moment is in this direction. Well, magnetic field is this direction. Torque is down. So what the needle will do? Spin like that. Right? Now let's see what will happen if we deviate slightly that way. If I deviate slightly, so magnetic moment now is in this direction. Magnetic field is this direction. Up. Torque is up. What the needle will do? Turn that way. Yeah, so what's the conclusion? They have to be in the same direction. Magnetic moment of an object is aligned from the South Pole toward the North Pole. Yeah, this is the direction of magnetic moment. Right. Now, considering actually that magnetic field vector, I mean, if I take a bar magnet, let's say that this is a bar magnet. I don't actually like to say that magnetic field vector is always oriented from North Pole to South Pole, or that North Pole attracts South Pole. But if I take a bar magnet, and if this is North Pole and this is South Pole, magnetic field lines will have this direction. So magnetic field vector will be, well, the lines will start at the North Pole and go into the South Pole. Inside, actually, I mean, the reason that I don't like it, because inside the line is still continuing through this through the magnet, and really inside it the line should be drawn from the South Pole to the North Pole inside the substance, but outside it is this way. Which magnetic pole do we have in Hudson Bay? South, right? magnetic field vector is directed that way, which means that over there is the south pole. The north pole of the needle is kind of attracted to that pole over there. Well, in the history of the Earth, it was not always the case. Occasionally, the Earth flips in magnetic field, and actually, the reason that the way that we know it is from the settlements of magnetic substances. Yeah, because think what will happen in the ocean nowadays if a magnetic substance, like a piece of a tiny piece of iron in the magnetic field will become a tiny magnet, weak magnet, but it will be a magnet, and it will behave like a needle. So think now in terms that you have a lot of needles in the ocean, and they slowly fall to the ground. How they will align themselves nowadays? Well, in water they are relatively free to turn around. So they will turn around with the north pole, with their north magnetic pole toward the south magnetic pole of the Earth, in other words, to the north pole of the geographic pole of the Earth. And so if it was like, if initially it was random orientation, it will get to this orientation and fall to the bottom. And a lot of those particles will fall to the bottom that way. Well, in the meantime, they will be covered also by all other material which falls to the ground. So nowadays, everything what settles on the bottom and has magnetic moment is heading with magnetic moment that way. So in a few million years, for example, if somebody takes cuts out some kind of a core or a cross section and will check the layer which was deposited now, they will discover that magnetic moments of all particles of all tiny pieces is this direction. So they will conclude that magnetic field at this time was heading that way. Well, we have done it to see orientation of the past particles, and we see particles which are oriented the other way. So magnetic field flips back and forth. And actually, I think one of the planets, I think Uranus, I'm not sure, though, at this moment has poles on the equator. So it looks like it is in a flip of its magnetic moment. All right. But I don't think that we can use this planet for engineering purposes. However, for engineering purposes, we can take advantage of the fact that objects have magnetic moments. Let's take a look at magnetic moment of a current carrying loop. We figured out that the force exerted on such a loop is 0. Let's say that this is magnetic field, and I have a frame in which current flows in this direction. I mark orientation of the frame by the vector which is normal to the plane of that loop, and this normal vector makes angle theta with the magnetic field. I mean, for simplicity, let's imagine that both magnetic field and this normal are in the plane of this drawing. So this side and this side are parallel to the plane of drawing. Now this side and this side are perpendicular to the plane of drawing. So let's figure out the forces and the torques about the center of mass of this object. So let's start. How about if we start with this? Oh no, maybe this one. Maybe this piece of wire. And so we have current, and we will have to use this formula which we use for a piece of wire. So we have to multiply IL current vector L, which is drawn from the end, from one end of the wire to the other end of the wire, consistently with the orientation of the current. So IL is in this direction. Our magnetic field is up, well, kind of at an angle. So magnetic force is toward us. Magnetic force exerted on this piece is toward us. And the center of the force would be, I mean, from symmetry, we can recognize that the center will be along, well, at the middle of this piece. So force is in this direction. What is torque about, what would be the torque about the center of the loop due to this force? Well, position where the force is applied will be indicated by this vector. And then the force is in this direction. The two vectors are parallel to each other. Therefore, torque is going to be 0. Recall that torque is equal to the product of position where the force is applied, so position of the center of the force multiplied by the force. So torque exerted on this piece is 0. Well, we can figure out that the torque exerted on the other one is also 0. Now let's think about these two. So this time, or how about if we think about this one? So current is flowing this direction toward us. Magnetic field is upward at slightly at an angle. So magnetic force is slightly to the right and upward, like on the drawing over here. And I marked it, I mean, this is the force exerted on the entire piece. Again, I used symmetry and concluded that the center of the force is in the middle of the piece. And now what is the direction of the torque resulting from this interaction? And so here, position of the center of force is here. So the position vector is in this direction. Now force is in this direction. Product of those two is in. So torque resulting from this force is into the drawing in this direction, parallel to this wire. Well, if we repeat the same analysis, we'll figure out that this force is slightly downward. So now position vector is in this direction. Force is slightly downward. I conclude that torque is again in. Both torques are in the same direction. Torque exerted on this side and on this side are in the same direction. I'll mark it. Yeah. So we can figure out that the resultant magnetic torque on this loop is in this direction. So if I grab, let's say it's not rectangular loop, but doesn't matter. In this configuration, if I thought about this loop, so current, imagine that current in the loop flows this way. And magnetic field is this way. We figured out that torque is going to be in. Magnetic torque is going to be in, which means that magnetic field will try to rotate this loop which way? This. Right? It will try to rotate it this way. Let's be a little bit more formal and evaluate the value of this torque. Well, I have torques resulting from four from four sides. We figured out that two of them are 0. The other two will depend on the dimensions of the of the loop and the value of the current and the value of the magnetic field vector. All right, so these are the ones which are zeros. Now the ones which are not zeros, well, if I take A over 2, it's the distance from the point about which I calculated the torque to the point where the force is applied. Now, current flowing times the length of this piece times magnetic field vector will give me the magnetic force exerted on this piece. And yeah, so this is the, well, magnitude of the position vector. Now with this, I mean, it's not precisely what I'm saying. Well, no, actually, I mean, with introduction, I used already this n vector to indicate the direction as well. So this first term, actually, I don't distinguish the two terms. They are identical, and these two are the torques, not magnitudes. These are the torques. So taking care of this, I mean, this vector product indicates the direction. You can check that normal vector multiplied by magnetic field vector will give us a vector in this direction, indeed. Now, I can recognize that that here I have a product of one dimension of this rectangle and another dimension of the rectangle. Well, it is going to give me area of the rectangle, right? And if I combine it with this unit vector, I will get a vector which is perpendicular to the surface and whose magnitude is equal to the area of that rectangle. What did we decide to call this type of a vector? We have already introduced a name for it. How did we decide to call it? A surface vector. Like a segment vector was a vector whose magnitude was equal to the length of the segment, and the direction was consistent with the orientation of the segment. Surface vector is a vector whose magnitude is equal to the area of the surface, and its direction is consistent with the orientation of the segment. All right. We made here a conclusion that magnetic field vector, magnetic moment exerted on this loop is equal to the product of current and the surface vector with magnetic field vector. What is then magnetic moment of that loop? Flip your page back just one step and see how magnetic moment is defined. Magnetic moment is defined in such a way that the magnetic torque is supposed to be equal to the vector product of magnetic moment of the object and magnetic field vector. Now, if we take a loop, magnetic moment is equal, magnetic moment is equal to the product of, the product of this vector and magnetic field. So, what is from this we can conclude that magnetic moment of the loop is equal to the current flowing through the loop multiplied by the surface vector. All right, before I go to this, how about if I show you a demonstration, because it has important application. Let's see. Well, I assembled here a device. Well, actually, here is a very, very neatly wound loop of wire. Actually, there's a lot of those loops. And well, right now, it is actually connected in two different ways. One is, it is connected, these loops are connected to these two pieces of metal, and they are, well, like a tube which is cut over here, on this side and on this side. So here we have two isolated pieces of a full ring, and each of those half rings is connected to that loop. This arrangement of those half rings is called a commutator. And it is called a commutator because now I can make it, when I put it on in here, depending on the orientation, I can run current one way or the other way through the loops. Yeah, these two parts of the commutator touch pieces of metal which slide actually on those rings. They are called brushes, and potential difference is created by the power supply between the two brushes. So the two brushes provide current to the loop, and every half a turn the current changes its direction. Because now magnetic field, here I have one pole of a magnet, and here I have another pole. So magnetic field is in this direction. Now, let me think about a bigger one. Yeah, so if I have magnetic field over here, and let's say that I have this loop at an angle, and magnetic moment is in this direction, which means that current will have to flow this way in order to have magnetic moment in this direction. So with magnetic field in this direction, magnetic moment in this direction, magnetic torque is going to be up. Do you see that? The magnetic moment, magnetic field. Vector product of magnetic moment and magnetic field would be up, which means that, well, there is practically no other torque. There is a frictional torque, but magnetic moment will turn the loop this way, aligning magnetic moment with the magnetic field. Well, what the commutator does, it changes. So right now magnetic moment is in this direction. What the commutator does, it flips the direction of the current. So current now, instead of flowing this way, starts to flow the other way, creating magnetic moment in this direction. Well, it still has some inertia, rotates further, so magnetic moment now is in this direction. Magnetic torque is up. The loop turns. At this instant, commutator changes the direction of the current, flips magnetic moment. Magnetic torque is still up. And this way, we make a motor, which is a DC motor, and then it is supposed to rotate. So how about I turn on this voltage? Right now I'm applying just 2 volts. I have to help it a little bit, and you can see this current, this motor turning. Now see what will happen if I increase the voltage applied to the motor. Now it's 3 volts, 4 volts, 5 volts. I'll go down because soon it will fly away. So increasing voltage applied to the motor caused something. What? What was happening? It was speeding up. Correct. I mean, I have a device actually. This is called a strobe. If I turn it on, it blinks. I can use a strobe, for example, to determine how fast it rotates, which I'm going to do now by assembling a different type of a motor. Because, well, important thing is that in the motor, the magnetic moment flips at the right instant. Yes, as it turns, whenever the plane of that rotor or of that loop is perpendicular to magnetic field, we have to make sure that magnetic moment is opposite to the direction of the magnetic field, because then the magnetic torque will be not zero and it will be flipping or turning the loop. But now, instead of using commutator, I'll use a current which actually flips its direction. What kind of current would I have to use? AC, correct. So, commutator would be redundant now. Rather than using the commutator, I use this side, which has just 2 rings and 2 complete rings. And each of those rings now will be separately connected to the power supply through the brushes. All right, now I'll go to the sinusoidal current. All right, and now it is 15 hertz. All right, and now the motor turns. And actually, to see how fast I will use now the strobe to see how fast it turns. Sam, can you maybe turn off the lights? Yeah, because now I will have to adjust this frequency to such that it appears that I have just fixed rotor. Do you see that it's not turning now? It appears that it is not turning, but it appears only because you see at the instances when the lamp flashes. And look at the frequency at which it flashes. It's exactly 15 hertz. Now what will happen if I increase the potential difference? Guess what will happen then? If I now apply, instead of 5 volts, I put 6 volts. Now it's 6, 7, 8. Maybe it's not turning. Ow! No, it was turning. Now it isn't. Oh, it's turning. Yes. Yes, Sam, can you turn on the light so that everybody can see that it's still turning? See, it is still turning. Now, what was happening as I was increasing the voltage? What was happening to the rate at which it rotated? Nothing, right? Now, so now how fast motor rotates is not determined by the potential difference, but by the frequency. Actually, let's see it. Yeah, so I will increase now the frequency, let's say, to 17 hertz. And Sam, why don't you turn off the light again? Yeah, so we see that it doesn't rotate at 15 hertz anymore. I think that's it. Yeah, so it rotates now exactly with the frequency which we set up. All right. Thanks. This type of a motor is called a synchronous motor. It rotates at a particular frequency determined by the frequency of the current flowing through it. All right. Now, just one more subject which I would like to discuss is that if we place a magnet or an object which has magnetic moment in magnetic field, then there will be magnetic potential energy associated with it. And magnetic, I mean, I'm not deriving this formula. In principle, I would have to see how much work is done if we move an object to a particular location. Now, this time, actually, it is dependent. Magnetic potential energy depends not only where the object is, but what is its orientation. So if we turn the object, magnetic potential energy is going to change. Let's now try to figure out, or how about if we put the needle in magnetic field, and let's say that how the magnetic energy is changing. So let's say that I'm not moving magnetic needle through space, but I'm only rotating it. At what orientation magnetic potential energy would have the lowest and the highest value? Well, in other words, what will be the lowest and the highest value of this product? What product do we have here? Which one? Dot product, scalar product, right. So we take two vectors, multiply them, and the result is going to be a number. All right, so at what orientation the number which we obtain is the smallest? Let's recall now how we calculate the scalar product. So I can take magnitude of this vector, so magnitude of the magnetic moment times magnetic field strength and times cosine of theta, which is the angle between magnetic moment and the magnetic field vector. All right. So when the product will have the highest and when the product will have the lowest value. Let's start with the highest value. When the product has the highest value for a given magnitude of magnetic moment and given magnetic field strength. When they are parallel. Then when magnetic moment and magnetic field vector are parallel, the product will have the highest value, which means that because we have here minus, it would mean that the magnetic potential energy would have the lowest value at this particular location, just due to orientation. Now, what will be the highest, in other words, the lowest value of the product? When what? When they are perpendicular, because then cosine assumes the lowest value, right? What is that lowest value? 0. I disagree. I think that cosine can be smaller than 0. It could be -1, right? All right, so the smallest value is not when they are perpendicular, but when they are in the opposite direction. When magnetic moment is opposite to magnetic field vector, this product has the lowest value and potential energy has the highest value. So this is how orientation affects the magnetic potential energy. Now, how position affects. So let's say now that I move this needle without changing its orientation. At what place magnetic potential energy would have the highest value, and at what place it would have the lowest value? Well, so now the angle doesn't change. Magnetic moment of the object doesn't change either. Well, the only change which changes is magnetic field strength. Over here, for example, we see that at this point magnetic field is stronger than that point here because the lines are closer. So this is not uniform magnetic field. If magnetic field is uniform, then you can see that it doesn't matter where, that only orientation affects potential energy. But if magnetic field is non-uniform, then potential energy is also a function of the position of the needle. And where we have stronger magnetic field, actually we can have either, I mean, this needle, for example, when magnetic moment is kind of parallel to the magnetic field lines, then the closer to the closer the line where the stronger magnetic field is, the potential energy will be lower. However, if North Pole was here and South Pole was here, if we move it over there, actually potential energy would be increasing. All right, so this will be all for today, and see you